All right, let's take a look at how to do some calculus with our new vector valued functions. Just like in Calc 1, the first thing we're going to take a look at is how to take the derivative. So if you remember from Calc 1, f prime of x by definition was the limit as delta x goes to 0, f of x plus delta x minus f of x all over delta x. Well, guess what? It's going to work the same for our derivative of our vector valued function. R prime of t is going to be equal to the limit as delta t goes to 0 of r of t plus delta t minus r of t all divided by delta t. All right, so it looks like a mess here, but this ends up working out exactly like you would expect that it would. Basically, all we're going to do is we're just going to take the derivative of each component of this. So another way to look at it is r prime of t is just going to be x prime of t, comma, y prime of t. And if there's a z component, z prime of t. So very, very easy to do. So kind of an example, find, let's say, r prime of t, where r of t is, I don't know, t squared e to the t. So r prime of t, the good news is, again, your intuition works exactly the way you would. Just do the derivative of each component, and you're done. That's it for finding the derivatives. Now, since it is a derivative, it does go by pretty much all the same rules a derivative does. I believe the author is going to, at least Larson here, is going to introduce a notation that you may not have seen for the derivative. We've seen the prime notation for a derivative, and you've also seen, excuse me, a differential notation for a derivative. But what you may not have seen is you can also write the derivative using what's called the big D notation, or operator notation, to where this, you put the big D, of course, out front. This tells you what you're taking the derivative with respect to. So this is the derivative with respect to t of r of t. So if you see this, don't be confused too much about it. That is just a derivative. Let's take a look at just a couple of properties. I'm going to use this notation because I believe that's what he uses in the book, just so you get used to saying it. What happens if you take the derivative of a constant times a vector? Well, like always, since it is a derivative, well, that constant can come out front. So that would just be the constant times the derivative of the vector. What if we're doing, again, nothing's really going to change here, r of t plus or minus some other vector s of t? Well, that's just the derivative of r of t plus or minus the derivative of s of t. Again, all to be expected. Now, where it gets a little interesting, and it's really not that confusing. Let's say if I had some u of t, r of t. All right, now notice here, I don't have a vector symbol on my u here, which means this is just a function of t. Kind of like if I had the square root of t times t squared e to the t. Right, that's just this function times the square root. So, since that's still multiplication, your product rule still applies. So you do the derivative of one at a time and then find the sum. So that's going to be the derivative of the first function times r of t plus the derivative of the second function times the first. So that's one way you can have multiplication, but now that we have vectors, we have two brand new types of multiplication. We have the dot product and the cross product. And well, it works the same way. I'm going to use, let me do r's and s's. So if I had r of t dotted with s of t, that's still multiplication, so the product rule still applies. It works exactly the same way. Derivative with respect to t of r of t dotted with s of t plus the derivative of the s of t dotted with r of t. And notice, whatever the multiplication was here is the same multiplication that was on the other side. This was the dot product, so we kept the dot product, which means if we have r of t cross s of t, still a product, the same thing applies, except for now, cross s t, and d of t, s of t cross r of t. All right, so there's some of our basic properties. I'm sure the book gives you more, but the idea is everything that we learn in Calc 1 is the same, but we do have multiple different types of multiplication. But since they're all multiplication, they all actually go by the exact same rule. All right, let's go back over here. So derivatives are very straightforward. They work exactly the way that we would think. The good news is integrals do too. With only one small change to a very small piece. So if I ask you to find the integral of some r of t dt, that would be the integral of some, that's not what I'm right, some x of t, y of t dt. Well, exactly what you would think, you're just going to do the integral of each component with respect to t. Okay. Now, of course, if there's a z component or ever how many they are, you just integrate each and every component. Now, this is exactly the same as if you have bounds. The bounds really don't change anything. And I'm just going to not write that next step. This is just going to be the integral from a to b of x of t dt. And the integral from a to b of y of t. All right, so let's take a look at this and see the one weird kind of thing that comes out of this. And it's when we're dealing with indefinite integrals that it's a little bit interesting. Let's do something real simple. Let's say I gave you an r of t was, I don't know, e to the 5t comma t cubed. And I said, find the integral of r of t. Okay, so just by definition, this would be the integral of e to the 5t t cubed dt, or the integral of e to the 5t dt, comma, the integral of t cubed dt. Well, we should know to do these quickly by now. This is 1/5 e to the 5t plus some constant, right, our integration constant. This is 1/4 t to the 4th plus, well, a different constant. So I can't call them both c because they got to be different numbers. So I'm going to call this one c1 and that one c2. So this is a perfectly fine way to represent this. However, you could actually represent it slightly different. Because of the way that we add vectors, I could write this as this: 1/5 e to the 5t, comma 1/4 t to the 4th, plus the vector c1, c2. Right? Because you just add the x components and the y components together and you get right here. Now, another way of thinking about this, instead of adding an arbitrary number to each one of your integrals, you can add an overall arbitrary vector constant to this. So another way to represent this would be 1/5 e to the 5t, 1/4 t to the 4th, plus some constant vector. So the c with the vector thing on top just means that's a vector full of arbitrary constants, which you could label, any way that you wanted to here. Now, where this, the arbitrary constants come into play, like always, is if we wanted to find a specific function, we'd have to know something about the original function. So if I said find r of t here, what if I also told you r of 0 is equal to the vector 2, 7? So by giving this little bit of extra information, we can actually figure out what this arbitrary constants are for this. It doesn't matter which form you put it in, I'll show you just visually how it looks. Let's start with the first way we did it, because a lot of students like it like this. So this was our vector, I'm going to go right over here. This was our vector r of t, once we integrated. Oh, I'm sorry, this was our integral of r of t. But let me do this. Let me change the notation here just a little bit. Fun. Go back and call that r prime. I don't want to come up with the whole new example. Just call that r prime, right? So if we integrate it, we get r here. So this is the integral of r prime of t, or r of t. So if I know that r of t, what did we say it was? It was 1/5 e to the 5t plus c1, 1/4 t to the 4th plus c2. So r of 0 would be 1/5 e to the 0 plus c1, 1/4 0 to the 4th plus c2. That would have to be equal to the vector 2, 7. So this is the vector 1/5 plus c1 comma c2 has to be equal to the vector 2, 7. Well, for two vectors to be equal to each other, their components have to be equal. So for the x components have to be the same, so that has to be a 2. And the y components have to be the same, so that has to be a 7. So all you got to do here is solve. So c1 is equal to, that's 10/5 minus 1/5 would be 9/5. We can already see what c2 is. So our final function, our r of t, we could write as 1/5 e to the 5t plus 9/5, comma 1/4 t to the 4th plus 7. Okay, so if we're given some initial condition, some value that we know about, we're able to figure out what those arbitrary integration constants were. Now, this is the way a lot of students like to try to figure it out, but you could have also done it like, we'll go this way. We could have used this form down here. What if I had said this, that our r of t, 1/5 e to the 5t, 1/4 t to the 4th, plus the vector c1, c2. If we were to express it like this, it's really going to work the same way, just expressed a little bit differently. So r of 0 would be, just like before, 1/5 when you plug it in there, because that's going to be 1 and 0, plus c1, c2 has to be the vector 2, 7. So if you see to solve for c1 and c2, all you have to do is subtract that vector from that side. So c1, c2 is equal to 2, 7 minus 1/5, 0. And we know how to subtract vectors, so c1, c2 is equal to the vector 9/5, 7. So now if we wanted to represent our answer, another way to write it is r of t was 1/5 e to the 5t, 1/4 t to the 4th, plus 9/5, 7. So either one of these two representations would be correct. Either way of finding those arbitrary constants would be correct. It was just whatever you seem to like the best. All right, so here we learned how to take derivatives and integrals of vector-valued functions. The idea is really straightforward. You just either take the derivative or integrate each individual component. Now, if you're talking about you want a higher order derivative, like the second derivative or third derivative, well, just keep taking the derivative. It's exactly the same. Or if you wanted to integrate more than once, just keep integrating. All right, that's going to finish us up for this. Next time, we're going to see how we can use a little bit of these ideas to come up with some applications.